Hit record. It's recording. Okay, good morning, everyone, for our distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Mohammad B. Shadmand, Assistant Professor and Director for Intelligent Power Electronics at Grid Edge Research Laboratory, Department of Electrical and Computer Engineering at University of Illinois, Chicago. The title for today's talk is Empowering Power Electronics, Dominated Grid Resilience and Cybersecurity. Dr. Mohammad received a Ph.D. degree in electrical engineering from Texas A&M College Stations in 2015. From 2017 to 2020, he was an assistant professor with the Department of Electrical and Computer Engineering, Kansas State University. Since 2020, he has been assistant professor with Electrical and Computer Engineering and director for Grid Edge Research Lab at University of Illinois, Chicago. His current research include resilient control of power electronics dominated grids, resilient self-driving grid, collaborative control architecture for network of grid following and grid forming inverters, applications of machine learning techniques for inverters, dominated power systems, situational awareness and intrusion detection systems for power electronics and smart grid. Dr. Mohammad has published more than 160 journals and conference papers, 3 book chapters, and his research grants and industrial projects are backed by more than 16 million in funding from sources such as DOE, NSF, Qatar National Research Fund. Dr. Shadmand is a senior member of IEEE. He was a recipient of Michelle Munson's Serban Simu Keystone Research Scholar Award, Kansas State University in 2017 and 2019 IEEE Myron Zucker Faculty Student Research Grant. He was also a recipient of the 4 Best Paper Awards at multiple different IEEE conferences. He is the General Chair of the 50th Annual Conference of the IEEE Industrial Electronics Society, Chicago in 2020. He also served as a guest editor for a special section on AI and machine learning applications in smart inverters for IEEE Journal of Emerging and Selected Topics in Industrial Electronics. Dr. Mohammad is also an associate editor for IEEE Transactions on Industrial Electronics and IET Renewable Power Generation. It's a great honor, Dr. Mohammad, for having you as part of the at UND's Distinguished Webinar Series. We are very pleased to have you here, and thank you so much for joining this morning, and the floor is yours.
Thank you very much, Dr. Prakash, for inviting me. It's a pleasure to be here and present some of the research activities that we are doing on power electronics dominated grids in terms of the resiliency and its cybersecurity. Just checking, can you see my screen now?
Yes.
Okay, all right, so just let's see. All right, so well, as Professor Prakash introduced me, I don't need to go over that. I can skip the first slide here. It is on empowering power electronics dominated grid resiliency and cybersecurity. Let's go to the next slide. Yeah, here is some information about me here. So all of this, my background, Dr. Prakash went over that. Thank you very much. So I just want to share a picture of my research group on the right in fall 2022. Some of my students graduated already and now working in industry and other research institutes. Well, I like to appreciate their inputs and contribution on my today's presentation, and it's basically my PhD students' research that I'm going to present today. So talking about cybersecurity of the power grid, I usually start by looking into some real events, real examples here for those who may not believe in like a cyber attack on the power system. It could be a reality and it's actually happening. So one of those most severe attacks or significant attacks that happened a few years ago, not very far, was on December 23rd in 2015 in Ukrainian power grid. That is one of the most popular cyber attacks events in the world, where it started around 3:35 p.m. local time, and 7 of the 110 kV and 23 of 35 kV substation were disconnected for around 3 hours, and that impacted millions of people in Ukraine. And several outages happened, and later studies revealed that three different distribution systems where distribution companies were attacked and compromised. I was watching some of the news footage a couple of days ago, and those distribution companies were just talking about like it was like a sci-fi movies, like Hollywood movies, that they have seen the computers and monitoring systems. They just all went out of their control and they couldn't do anything. So that's a reality. This kind of thing can happen also in the US, which already is happening. So several cyber attacks on the US power substations and power grid infrastructure are reporting daily around the world. I think it was a couple of years ago, there was a cyber attack on substation in NC State that create significant issues for utility companies in that area. The image that you see on the right of this slide here, although this is not because of a cyber event, but this shows like how a blackout could happen in the power grid and having a cascaded failure and resulting in a major blackout for other type of events as well, like the event that happened in the Texas because of the severe weather condition a couple of years ago in Houston area and impacted major, utility companies there, ERCOT. So several other type of catastrophic impacts and the blackout events are happening around the world. So the popular ones are the 2019 blackout in the UK, which affected more than 1.1 million customers. The South Australia blackout in 2016 affected 850,000 customers, and the Texas one that I referred to, which was the major one here, 4.5 million homes. So there are different reports discussing like what was the main reason of that blackout in February 2021 in Texas. So some of them are looking into frequency deviations and the impact of the wind turbines, and of course because of the extreme weather condition, the huge loading in the system, in the utility power system, initiate this kind of catastrophic event here. So what we want to discuss today is that like now, where are we leading to? Where are we heading to with the futuristic power system that are being basically introduced now, and the characteristic of these futuristic power systems. Are we going to make the condition worse, making the system more vulnerable or not? Well, the answer is that the system is becoming more vulnerable to this type of events, and which could be intentional or unintentional events. The intentional events, I call them like a cyber attacks, and unintentional events are those type of basically situations such as the weather condition, extreme loading condition, introduction of fleet of electric vehicles to the grid, and all of them, if it is not properly controlled and monitored, could have catastrophic impact on the resilient operation of the power grid. So the power electronics dominated grid, so-called PEDG, have three main characteristics here. One is the low inertia, which is due to high penetration of the inverter-based structure, and replacing basically the majority of the power generation that are currently by synchronous generator by the inverter-based generations. That will impact the inertia of the system, the low reactance to resistance XR ratio of the feeder, and the complex control system. Talking about the complexity of the control system, basically there are three main category of the control for PEDG system. One called centralized, decentralized, and distributed control system. So in a decentralized control system, which is basically the basic or control scheme with lowest complexity, it may be more basically easier to implement, but at the same time, it may not have an optimal, response to different kind of situation because of the local access only to the measurements, and there is no coordination aspect of it. But it has a lowest complexity. In a distributed control system, which could be the most complex, most expensive, and if implemented properly, could have the optimal response, but at the cost of more in communication infrastructure and more vulnerabilities that will be introduced. So one of the popular control structure that you can see at the bottom of this figure is hierarchical control schemes, which are centralized controllers that has multi-layer of controllers, primary, secondary, tertiary, and fourth layer controllers in some cases. And each of these control layers are responsible for certain control optimization, regulation, and coordination between the inverters. So a little bit more detail on this and type of control structure. The primary controllers of the inverters in the PEDG systems are usually taking care of the PQ. They are basically either the PQ control base or voltage control base, and they are have different functionalities such as like the islanding detection and other advanced functionality at the primary layer controller. These controllers are typically sampled at around a microsecond time scale. And the main goal of this is to provide switching signals for the inverters at the grid edge. The primary controller are getting input from a secondary controller, which is running at a slower time scale of milliseconds, would be up to the seconds also. And their goal is to provide perhaps voltage restoration, voltage support, and then taking care of the synchronization of these inverters, and then looking into more advanced functionality if you have an energy storage system in the PEDG, such as looking into state of the charge and other circuit breaker monitoring and so on. The tertiary controller is running much slower. It could be from seconds to minutes time scale, looking into global optimization of this. So as you can see, each of these, if compromised, each of these controller, if compromised, will impact, the inverter operation, the inverter generation, could create demand supply instability issues, could create, synchronization issues, and so on. So it is important that we have kind of intrusion detection system in each of layer of these controllers, and having a resilient control scheme for each of these. Well, of course, today we don't have enough time to go over, intrusion detection and, resilient control structure for each of these control layers. But let's start by looking into scenarios where the secondary controller is compromised and the primary controller needs to take proper action under, this situation. We want to see like how artificial intelligence, AI, and machine learning techniques can be utilized in order to make the primary controller more stable. So going into a little bit more detail of the key challenges in this PEDG, as I mentioned, the low inertia is a challenge here. The figure that you see on the right here, it shows that because of the low inertia characteristic of the system, the rate of change of the frequency, and the frequency is more vulnerable to this type of cyber events and other natural events. Also, like if some fault occurs, the angular stability of the PEDG also could be more vulnerable because of the heterogeneous nature of those inverters. So the impact of inertia variation is seen on the right with the 5 graphs that shows by blue, orange, and yellow, purple, and green. And it shows that adjusting the inertia and the coherency level of these inverters could impact really like the behavior of these inverters during the transient. That could happen due to any kind of severe events that happen, right? Other type of attacks that we that is important, and recently we start looking into that, are the stealthy attacks, which are targeting the low inertia characteristic of the PEDG. The stealthy attack, the way that we define that, are those type of attacks that remain undetected and until a tipping point happen, and then there's the state of the system start diverging. So the low inertia characteristic of the PEDG is introducing this new attack surface that may not have studied very well so far. And the reason is that some of the control signals may be attacked like at the primary control layer, while and the observable states, the supervisory controller and intrusion detection system are behaving normal until a point that the system start diverging and the inverters lose their synchronism and so on. So that is again a specific type of attacks that we are currently studying for inverter dominated grids, and that have not well studied in literature so far. So the other type of things that we need to look into that now, assuming that the blackout happened and the cyber attack was successful, then what? So how to minimize the power outage time? So we are talking about thousands of inverters operating at the grid edge. Resynchronizing these inverters and back to the normal operation, connecting them could be time consuming because of their heterogeneous behavior, because of the angle difference that the voltage angle difference of these inverters that needs to be synchronized before reconnection. That's another thing that we will show shortly. So talking about the inertia, this image here that you see on the slide shows briefly the concept of this inertia in the power grid. If you see, this is presented by some mechanical springs to show, like, what does inertia mean here. So in conventional power system, because of the synchronous generator and rotating mass that we have, naturally we have this like very high inertia in the system that make the system robust to some small changes, variation, and disturbances, intentional or unintentional disturbances, and so on. But in the absence of this synchronous generator in the future power grid and substituting them with the switching power converters, the inertia will be low, or in some cases, we can create some inertia by energy storage, utilizing the discipline capacitor of the inverters to create some virtual inertia and so on. So one research question that currently researchers are working on is how to basically optimize this inertia. Is it good to have high inertia, or are we looking for a better control system for the inverter? That's the question. Sometimes always high inertia is not desired because that impacts the restoration of the frequency as well. So looking into different prospect and challenges of emulating virtual inertia, there have been different inverter technologies and resources that are currently being integrated with the power grid for creating this virtual inertia. I mean, grid forming inverter controllers, they have different classifications, different controllers that can emulate virtual inertia. Among them are synchronous converter, virtual synchronous generator, Drupe controller, power synchronization control. Among these four main categories, Drupe controllers and virtual synchronous generator are the most popular ones here, where in the virtual synchronous generator, the inverter control loop is trying to mimic the dynamics of a synchronous generator by utilizing swing equation in the control loop and creating some virtual inertia according to the inertia constant that we are utilizing in the controller. Drupe controllers is a more linear based type of thing that can also emulate some virtual inertia by adjusting the Drupe coefficients here. There are discussions that we can have basically a duality between these two controllers and making them look similar by equating some of the coefficients in the controller. But the whole point here is that how can we utilize these inverters in order to create some inertia to make the grid a little bit more similar to the power grid that we have right now? It's still like our way to go. In a grid following inverter also, there are techniques in order to emulate the inertia, including the inertial PLL, phase-lock loop, power reserve control, artificial intelligence-based scheme that can be utilized in the control loop of the grid following inverters in order to mimic the dynamics of a synchronous generator, adjusting the set points of these grid following inverters by utilizing AI that is being trained from, let's say, synchronous generator behavior to adjust the set points of the grid following inverters to basically create some inertia. Well, all of this requires resources, right? So the inertial response requires some resources. This link capacitor utilization, energy storage system utilization, and battery energy storage system, utilization. Flywheel could be some other resources that create virtual inertia. So going a little bit into more details of how can we come up now with an attack resilient control system, assuming that you have a hierarchical control scheme. So one of the research that we have done recently, and the paper recently published in IEEE Transaction Industrial Electronics, is how to use basically how to use. Let me see if I can have a pointer here. There is no pointer.
There should be an annotator, I think.
Yeah, I want to. There is a laser pointer usually, since I don't see it here. Anyway, so I can show by my mouse here. So, so one thing that and one of the research that we have worked on is that how we can use artificial intelligence to integrate with the primary controller of grid following inverters, which is PQ controlled inverters, in order to come up with a self-driving kind of grid following inverter. What does this mean? This means that there at the early slide when I showed that there is a hierarchical control scheme that that needs to be implemented for this type of inverters to operate optimally at the grid edge. Can we eliminate somehow the secondary and maybe the tertiary controller by much faster primary controller only, which is based on artificial intelligence? So the idea, well, the question, well, is that if we can learn what the secondary controller is supposed to do by an AI, we can integrate that AI in the primary controller without requirement of communicating with rest of the grid, with rest of the inverters, with other controllers in the grid to come up with a local adjustment of the set points of the inverter set points by just looking into at point of command coupling of that inverter with the rest of the grid. So the challenge that we faced here is that a limited amount of data availability, how to come up with a data mining module, and then how to basically predict what the grid following inverter needs to basically do if there is some frequency and Rockoff variation at the grid edge. So the main features of this grid following inverter, I mean, this controller is to maximize utilization of grid following inverter. We are basically redefining the rule of the grid following inverter at the grid edge. And then we come up with a robust learned neural network to provide power reference correction for the grid following inverter during the transient periods without relying on the basically upper layer controller. And the application to cybersecurity here is that can we utilize this control scheme in order to minimize the amount of communication requirement for operation of the inverters under cyber attack, and then how to provide the real-time correction. So we show like some case studies here, but before that, we look into firstly the data mining approach. So in order to obtain the required data for the training process, we divided basically the data mining module into two basically sections: steady state and transient dynamic of the power electronics dominated grid analysis. So what we did here, we look into the power balance equation and we say that, well, I mean, this is basically the prevailing dynamic of the system. And then we start looking into the differential equations and solve them under different disturbances, small disturbances in the steady state and larger disturbances in the transient. So the full detail of the analysis of this steady state and transient analysis are available in the published paper that you see the reference here at the bottom of the slide. But the whole point here is that how to solve these equations and under different disturbances and different variation the parameters, such as adjustment of the inertia constant, damping factor, different load change, and different characteristic of the system that represent variation in the actual PEG system. How can we come up with a comprehensive data set? So that's the main goal here. So the data set structure here, or the goal was that the input to the neural network should be rate of change of the frequency and the frequency, which are the two inputs to the neural network. And then the output of the neural network is the PRF correction locally. So all we do here by looking at the point of command coupling of the inverter and with the rest of the grid, we measure the voltage, we obtain the frequency, we obtain the rate of change of frequency, and then the neural network locally will determine what should be the PRF correction without relying on the supervisory layer controller. So for those with inverter backgrounds, when say that, okay, like, then why not using grid forming inverter? Well, the grid forming inverters have the issues of, synchronization, power sharing between them would be more challenging, but the grid following inverter have a simplest, a simpler control structure compared to grid forming inverter. This is how we distinct between the grid forming and grid following inverter here. So we are trying to have a redefining basically the rule of the grid following inverter at the grid edge, while mitigating some of the drawbacks of the grid forming inverters by utilizing artificial intelligence here. So here are how the data set are created under different load changes, under different inertia constant, and then damping factor, and we try to see like what should be the delta P correction in order to convert the system to the delta F of 0 and Rockoff of 0, which means that there is no frequency basically a deviation from its nominal value. So in order to do the training, once this data set has built, we look into different approaches in order to optimize our training approach. We have found that the Bayesian regularization artificial neural network is a potential solution here that optimizes the training approach, and it avoids like overfitting, which is a real challenge in this kind of problem that we have because of the limited data set. Although, like when we created the data mining, we almost consider all the scenarios that could happen. We look into the wide range of basically constants or system parameters that could happen in real system. We tested that experimentally as well as in simulation, and refer to some realistic data set here to ensure the data set that we have is comprehensive. But again, in order to avoid overfitting challenges here, so we use this basically Bayesian regularization algorithm, which basically considers the weights probabilistic during the training, and the parameters of the prior distribution are basically modified on the Bayes theorem here for doing the training of the neural network. So the inputs, as it's shown here in this slide here at the bottom of the slide, are basically the f and df by dt, which is the frequency and the row count, and the output is delta p. So we look into different scenarios for here. So in order to validate our neural network, we look into an IEEE 14-bus system. So 4 synchronous generators are there, 7 grid following inverters there, and 1 relatively. This out of the 4 synchronous generators that are traditionally there, we remove them actually, and then we replace them by grid following inverter to make it 14-bus system dominated by inverters. So we kind of modify this 14-bus system and from its original version. And the total amount of loading in the system is 500 kilowatt, and 70% of the total loads are supplied by the DERs here. 2 different level of the voltages exist in this PDG, 13.8 kV and 380 volts. So we use transformers in the middle here to connect these 2 low voltage and medium voltage network together. So the idea for testing here is that if a couple of these DERs are disconnected from the grid due to some cyber event, due to any kind of other events, how the healthy DERs using the artificial intelligence locally can correct the frequency in the grid. So that's the scenario that we wanted to test here. So in the first aspect, then we look into more cybersecurity aspect of it. So in order to do this test and see like how much improvement we can have in the frequency response, we can see the figure A here is where the developed like artificial intelligence-based controller is disabled, and there is a 200 kilowatt loss of generation, which is a significant loss of generation, and see the nadir frequency here, which is 257, which would violate some of the standards here. And in figure F here, you can see also the row off is very high. It is 16 hertz per second, which is again violating some of the standards that we have. Then the next step is to enable the artificial intelligence on the grid following inverter 6 and see like if that grid following inverter, which is supplied by hybrid energy storage and solar, can correct the frequency locally without relying on higher level controllers. So what it does is basically adjust its power set point based on the local embedded neural network in the controller by looking at the frequency and rate of change of frequency and predicting the trajectory of these frequencies in order to adjust the reference set point of the inverters in a much faster way, even if we have a healthy secondary controller or a grid forming inverter that you will see in the next case study that we did experimentally. So as you can see here, the frequency nadir is now limited to less than 59 hertz, and the frequency is restored within 90 milliseconds here, which is much faster. And the rate of change of frequency that you can see in the figure F here is basically limited to 8.6 hertz per second. So the adjustment, the AI output is shown in the figure E here, where it shows that what is the delta P output of a neural network when this kind of disturbance is happening. As you can see, the delta P output is changed very quickly in order to basically make the grid more basically robust to these kind of disturbances and more stronger to these kind of disturbances that you can see. So here is our experimental validation test bed. So we validated that experimentally using a network of grid forming and grid following inverters that are disconnected from the main grid here to represent a more realistic PEDG here. The system parameters are shown in this table. So the idea here is that for the testing is first is that to disable the artificial intelligence and see if we have just grid forming inverter, how the frequency behavior looks like here. Of course, in our lab, we didn't have a synchronous generator to do. Otherwise, I mean, we would do that. But here, the grid forming inverters were able to restore the frequency after, a disturbance that occurred at the AC bus of the microgrid that we have in the lab. And the frequency nadir goes to 59 hertz, and there is a delta F of 1.43 hertz here, which is significantly large comparing to where we enable the AI in this slide here. And we could limit basically the frequency deviation from its nominal value to 59.9 hertz and the restoration time to around 400 milliseconds, which is much faster. So in this case, also, you can see that how superior is this AI based control scheme under this kind of disturbances when we basically compare that to grid forming inverters, which are usually responsible for voltage and frequency support of the power grid of microgrids, basically under disturbances. So now looking into a more basically a cyber resiliency aspect of this controller. So the scenarios that we emulated was that if the communication link between the secondary controller and the primary controller of such a system is compromised, how this AI can basically provide some delta P correction that is basically correcting the reference set points that are manipulated from secondary controller and reaching to the primary controller. So the attack vector that we are modeling here is shown on by this simple equation here. So we have a P tilde reference, which is equal to the actual nominal reference, which is coming from an optimization of the secondary controller, plus some G tilde, which is the manipulation vector here. And this P tilde is basically inserted into the control loop of the primary controller of the inverter that you see in the blue box here of the inverter. And the question is that how can we first of all detect such a manipulation? And then how, once detected, how can we correct it? So the correction is going through the similar kind of neural network that I just explained. So the input into the neural network could be the frequency and rate of change of frequency here, and the output here is delta P. So delta P will be a function of F and dF by dt here, which is the frequency and rate of change of frequency. And the question is that if we have some non-zero ng tilde here, like what should be the output of this delta P? So and in ideal situation, this lambda or delta P adjustment from the A&N scheme here should be exactly equal to basically G tilde if it can predict correctly. So we want to see like how this will happen. But before triggering basically the output of this delta P, we have a simple intrusion detection system here, which is again utilizing some artificial neural network here. The details are available in our published recent paper. But what it does basically, it looks into the trajectory of this frequency, and if it is violating some of this, the predefined thresholds that we have, it detect that or flag that power set point that coming from the secondary controller, and says that that should be corrected somehow. We don't label that as an attack, but it could be a potential cyber attack here where triggers this ANN module here that basically activate the delta P correction. So I'm not going over the detail of the training approach. It is similar to what I explained earlier for the previous case, but looking into some of the training performance result that we have relatively low average error for most of the cases, which is 0.0034. And for 1,000 epochs, the mean square error during 1,000 epochs was around 2.64 to the E-8, which is relatively very good, training results for the case that we have here. So here is a video of the simulation that we have done. So we have multiple inverters in this simulation. And in the first case, data jamming is happening from the supervisory controller here. As you can see, the figure on the left corner here is the active power, then we have the current, and then the voltage on the right and bottom corner here, and then the frequency on top. So what's happening here? A data jamming is happening. The frequency restoration is disabled by the grid forming inverter. And at this instant, the grid following inverters were not able to restore the frequency because they rely on the secondary controller that basically posed the correction requirement for the reference set point. So with that said, you see the frequency thresholds could be violated, and it could result in some cascaded failures and disconnection of the inverters. In the next basically case here is when we are enabling the detection system and the AI-based corrective scheme here. Similar kind of scenario is happening, but in this case, even without relying on the secondary controller of the grid following inverters, the grid following inverter were able to restore the power grid by basically mitigating the impact of the G tilde that is introduced into the power set points that are coming from the grid following inverters here. So this shows like how we can utilize artificial intelligence in order to basically make the power electronics dominated grid even with low inertia, with low inertia characteristic that make the system more vulnerable to this kind of disturbances, more robust to these disturbances actually. So now I will look into the control resiliency and like how to do restore the grid and how to basically detect this type of attacks on the power set points, and then how can we come up with a resilient controller if the supervisory controller of the PEDG power electronics dominated grids are under attack. The next thing that we want to briefly discuss here is that now once the attack is already happened, and then even in the worst case scenario there could be some blackout, and then these inverters that are connected to the grid edge are at the grid edge are islanded or shut down, and we need to have kind of black start. So we are talking about thousands of these inverters. So resynchronizing these inverters, reconnecting them to the power grid is a time-consuming process, and this impacts the power outage time. So according to U.S. Department of Energy definition on resiliency, we need to minimize the outage time here. So one of the other research that we have worked on that in the past couple of years is that how can we come up with optimization algorithms utilizing artificial intelligence in order to, and data-driven schemes in order to optimize or minimize the time of power grid restoration after a cyber attack that after and optimizing the black start, right? So in order to do that, we come up with basically two main step approach here. The first step, this is basically before going into that, this is like what I was talking about. Like under normal operation, all these grid forming inverters are connected to a single bus here, and then after an attack, some of them could be disconnected, and then we want to resynchronize them. This red box, red dotted box here, should reconnect basically to main AC bus of the power grid, and this requires that the voltage angle of them are being synchronized with basically the other grid forming inverters connected to the same AC bus. So in order to do this, we take basically two main steps. One is to have an optimal grid clustering. So the optimal grid clustering that we have here is to put the inverters that have more coherent behavior, they are highly correlated nodes into a single cluster. Here we apply basically singular value decomposition and affinity propagation approach in order to basically optimize these grid clusters, finding out the best boundaries for the grid cluster from perspective of highly correlated buses and coherence between them. Doing this clustering is a little bit more challenging for inverter-dominated grid. In traditional power system, the clustering have been there, but in inverter-dominated grid, because of the heterogeneous behavior of in these inverters, clustering them is even more challenging, and we need to consider a few other things as well. So in order to do this clustering optimally, we firstly try to enforce coherency between some of these inverters, putting them in a single cluster and making sure the boundary of the cluster are optimized based on the control tools and handles that we have. So we Basically, firstly, enforcing the coherency. The details of this again is recently published in IEEE Transactional Power System, and you can refer to that if you're interested to learn more about the optimal crossing. So once we have a clusters of optimally correlated coherent grid, now the question is that if some of these inverters that shown DER here are disconnected from each other, what can we do in order to resynchronize them optimally with minimum time requirements? So we'll go again into another optimization process here, and that is basically finding out an anchor angle for that particular cluster. What does that mean? It means that instead of like synchronizing them one by one, we find an optimal angle for a network of these grid forming inverters. And then we solve a min-max problem in order to basically optimize all the grid forming inverter to that optimal angle. What does it do? It says that one of the grid forming inverter could be like a super agent, could be an agent here. And then from multi-agent, system theories, then we say that, well, okay, all the inverters could follow that inverter and reach into that. So which inverter could be a super agent? That's the optimization problem that we do here. So we find out, we solve an optimization problem here to find out which of this, if one by one, building a matrix psi here, and you can look into the math of that in the paper that we recently published. So we look into basically the optimal angle that should be basically selected from these grid forming inverters, and then commanding the other grid forming inverter to follow that angle in order to minimize the synchronization time. In order to push the other inverters to follow that reference basically angle or the master grid forming inverter, we need to have a regulator here, which for us here is a PI regulator that is adjusting the delta P, adjusting the frequency of those grid forming inverter by injecting a P synchronization and a command into the controller, and that will change the phase angle of those inverters and merging those phase angles to the optimal or to the optimal angle. Once it passes certain logic algorithm that we developed, that making sure that they are the phase angle of them within the specified threshold, we can close the breaker of the grid forming inverter and resynchronize them after a severe contingency or cyber attack that happened and creating a blackout. So the last case study that I have here to share is like a scenario when we have a multiple virtual synchronous generators here connected to a feeder here, and the blackout happened. They are disconnected. The circuit parameters are and the converter parameters all presented here. All the inverters have their own unique distinct parameters here to make the system more realistic. Different filter parameters are considered here. Different ratings are considered here in order to show what will impact the synchronization. We do the evaluation in two ways. The first evaluation is that we assume that like a classical approach, that one inverter, all the inverters are tried to synchronize one by one to one of the inverters without looking into the optimization and the clustering here. And it took almost 83 seconds for resynchronizing these inverters into basically the main grid forming inverter that was targeted as one by one synchronization, which is very time consuming. And this is like would exponentially increase as we have more number of inverters, like 1,000 inverters in a grid. Now, with the proposed approach that we have developed recently, we look into the scenario where that we find the optimal anchor angle in that grid cluster that is coherent, and then all the inverters simultaneously merge to that optimal angle from the master agent grid forming inverters, and then after that the angle difference, the phase angle difference are meeting the minimum threshold requirement. We close the circuit breakers and we restore the grid to normal operation. So with that, we could significantly decrease the synchronization time to around less than 10 seconds here, which is a significant improvement for post-attack situation. So some closing remarks and research roadmap here is that we need to look into solution to detect and classify anomalies in power electronics dominated grid. Means that coming up with some data-driven approaches that look into real-time detection of those anomalies and classifying them from regular power electronics failures and other power system failures in the power grid. That's an important aspect. Like some of my other and some other, some of my students are working basically on that aspect of real-time AI-based anomaly detection. Solution to realize attack resilience and minimizing the attack reference, so optimizing the inertia in the power grid is one thing to consider here. Coming up with attack resilient, control scheme with minimal communication, like the AI-based approach that I mentioned. There are more things to do in that aspect, to consider the voltage restoration and consider the impact of, reactive power in the frequency restoration in basically power electronics dominated grid. And looking into also the impact of the other inverters, and they are also having the same AI module on each of the other inverters. So the interaction between them also is important. How to train them is a challenging task. So that's something that we are currently working on that in another project. So mitigating the attack impact and corrective action, looking into event-triggered self-learning controllers, post-attack optimal black start, and so on. So a summary of all of these, trends on power electronics dominated grid are summarized in this recent magazine paper that we published towards intelligent power electronic dominated grid via machine learning. That I encourage you to read, have a look at that. I would like to acknowledge our the funding agencies that supported this research. And finally, I would like to invite all to submit your papers to the IECON 50th IECON conference that we are organizing in Chicago, and the deadline for the paper submission in April 15. We have a special track on cybersecurity, power system, smart grid, and AI-driven approaches. Thank you very much, and if you have a question, I'll be happy to answer.
First of all, thank you so much for the fantastic presentation, for sharing your great research work that your team is doing. Appreciate for taking the time to do this. We'll open it for questions, so Jamison can collect questions, and maybe I'll start with some couple of questions. And I think you covered a lot of aspect of different concepts here, but I think maybe how do you see how are the attack vectors are different when we look at grid forming versus grid following in inverters, and the second part of the question is, you actually said you're using, most of your work is actually how AI has been used as a solution to bring regulation with frequency or synchronization. But how do you see, AI as a threat as we see more and more DER are going to be, penetrated into the grid, so it's kind of, how do you see this trade-off between use of AI and maybe, how AI could be a vulnerable attack vector in terms of things. So any thoughts on that?
Yeah, so these are very good questions, excellent questions. So the first, regarding to the first question, so like how different could be the attack vector in grid following inverters and grid forming inverter? It comes back to the structure of these inverters, control schemes. So in grid following inverters, as you may know, there are current control inverters that require some active and reactive power set points from some upper layer controllers, from a secondary controller that should be transmitted through some communication medium into those grid following inverters. So a potential attack on these, inverters, the grid following inverters, could be attack on the PQ set points of the inverters. It could be attack on the sensors of the inverter itself. So the current sensors, the voltage sensor of the inverters itself. This could be like two type of attack vectors that can happen on grid following inverters. In grid forming inverters, depends again on how we are implementing the controller for grid forming inverters. If you are looking into very basic grid forming inverters that are completely decentralized without any kind of synchronization scheme, they are more robust to attack. Could be because there are no or minimum communication requirements. But most of the cases, there should be some type of coordination algorithm, coordination control loop for this grid forming inverter, such as the one that I presented here. Now we need post black start, how to post cyber attack, like how to resynchronize them, exchange of the phase angle information in order to have more resilient operation and exchanging other information. So the attack on the grid forming inverter could be attack on, for example, the information are being exchanged between these inverters, such as maybe the phase angle, such as the state of the charge of the batteries that are connected as a source of this grid forming inverter. So to just summarize this, the attack vectors, the difference between attack vectors on these two classes of inverters are basically depends on what are the basically the control signals for each of these inverters, and there are not hundreds of different control schemes for these inverters going on. Answering to the second question, that's a very good question. So AI, if it is trained very well, it could be excellent. If not, that could make the operation of the grid miserable. So that is 100% true. We in fact looking into some type of attack vectors that are reinforcement learning based attack vectors that is using a digital twin of the power grid in order to learn an attack vector and then attacking the AI. So it's basically fight between AIs. So in this kind of the case, we are investigating what will happen here, particularly in the stealthy attack type of the system. So assuming that the attacker have an approximate knowledge of the system that can build a digital twin of that system. And then utilizing reinforcement learning, understanding adjusting basically these control signals or manipulating these control signals, how this impact the operation. It's actually fight between the AIs. We'll see what would happen in the future. So.
Thank you. I know we have another question from Dr. Utku Kose. Great presentation, Dr. Mohammed. Thank you very much. I would like to ask, what do you think about potentials of human-in-the-loop approach to be applied in PEDG? I feel it has a potential for resilience, but would like to hear opinions.
Yeah, that's very important and also question here. Actually, in our recent project from the OESIS office, we are looking into that. It's just started this January here, so we want to look into the impact of the human in the loop with noise schemes. And that could be one of the answer. Like if you are utilizing the AI and then we have a human in the loop, that can add additional layer of monitoring and situational awareness. So we did not look into details of that, but that is a very potential and futuristic approach for improving the resiliency and cybersecurity of the power grid, particularly saying that we don't 100% rely on the output of the AI, and then we have more redundant. It's basically talking about the redundancy, and the more redundancy that we have in terms of generation, backup, intrusion detection system, and the correction algorithm. That can bring more resilience to the power grid. But again, coordination, among these schemes is important, aspect to consider.
I know I like one of your slide that had, something like physical and cyber layer, and you talked about some agent-based self-learning control framework. And could you talk about, what do you mean by dynamic cyber cluster? Are you, a kind of, I see that there's some kind of agents, you're treating.
Oh yeah. So that's an image from like a part of a bigger project here. So what we are trying to say, we say that in the power electronics dominated grid, unlike the power grid, we don't have only basically a physical clustering of the power grid. We need to look into cyber clustering. What does this mean? The cyber clustering means that if we have a type of, let's say, a distributed multi-agent controller, like do we need to 100% align the borders of the cyber cluster with the physical layer cluster boundaries, or it should be the cyber layer cluster could cover two or more physical layers. So that's basically what it means in a multi-agent systems project that we're working on. And the reason is that we say like this should not be aligned is because of, again, like exchanging the necessary data for optimal coordination, synchronization of this, just in case we need to merge two physical cluster. Physical cluster, it just means that, when there are some, transient, some disturbances in the power grid, the frequency response of them, or how this inverter behaving coherently, and like what is basically the correlation between these buses. In the cyber clustering is basically saying that if we have this orange area on top here and we have the information for each of these inverter as an agent in that orange cyber cluster, can we have an optimal synchronization operation between these inverters? So that's what it means by this image. I'm not sure if I answer your question here, but this is what it means. Yeah.
Thank you. I know that some of your case studies are at 14 bus systems, but as we scale the networks to much more larger penetrations of DARs, and I have two follow-up questions on this actually. Have you looked into IEEE 1547 requirements and looking at these multiple communication protocols, IEEE 2030.5 and Sunspec communication? How do you see, I'm only speaking from attack vectors, point of
Yeah.
view. Has your research group has focused on specifically on these communication protocols, and also bringing cloud into the picture when
Yeah.
we're really looking at a larger collections of smart inverters and people, there are lots of other papers and coming up, and people have their own way to say what does resilience mean for as we see smart inverters. Yeah.
Yeah, these are very good points. Some of these research are really at a very early stage, particularly the AI one that we have on the 14 bus system. The reason is that, as you pointed out very clearly, like, scalability is a challenge here. The reason is that, now we are considering only one of those inverter equipped with AI. If multiple of those inverter equipped with AI, can they really go without communication? That's the challenge here. So do they need to basically have another layer of AI coordination for, coming up with to avoid any, adverse dynamic interaction of these inverters? So scalability is an issue. So we are working on that right now on a higher number of nodes, higher number of buses, scaling these. One approach, one measure that we are taking to mitigate the impact of, larger network is the clustering approach that we mentioned here. So just clustering them in order to, again, reduce the system to a smaller size, and training and so on. Looking into the standards and protocols, yes, we are looking into that, not particularly on this inverter application, on a solid, resilient solid state substation that we have. That's more hardware based, that we are collaborating with a couple of other institutions on that project. So we are looking into like different, security protocols that should be implemented. It's purely hardware-based cybersecurity project. So we are looking into that aspect. On the cloud base, we did not look into that, but that's an interesting thing to consider in this domain of research here. So
Yeah,
we'll be looking into ways to collaborate on that area.
yeah, that's what we are putting our efforts on, the more on the cloud aspect
Yeah.
of it. But yeah, maybe I think we will find a way to work with you
Yeah.
and as you. Great. Looks like Jameson, do you see any other questions coming on your end?
No, you answered them.
Okay. Um, Maybe I think this correction factor that you talked about, delta P, and how frequent one should actually envision that, and is it like in your case, is how are you doing it, and in a realistic system as we see a larger test bed or grid, what is your advice on that?
So that correction, well, that's a very good point here. And so it all depends on basically the outcome of, the ANN that is predicting the trajectory of the frequency. So our goal here is that to once this frequency and the Rokov trajectory is predicted, we keep them within the threshold, predefined threshold. So that's basically how often this should be updated. So it should, for example, have keep updated fast enough to keep the frequency, let's say between like 58.5 hertz to 61.5 hertz according to IEEE 1547 standards, and just being able to restore the power grid within 1.5 line cycle in order to avoid any tripping of the inverters and so on. So here we are basically running this outer loop controller, that is this correction here, 10 to 20 times slower than the primary controller inside, to avoid any kind of a stability concern and issue. And also looking into some basically um, uh, mitigating the impact of some of the noises that could happen. Particularly, we are talking about the derivative of the frequency, which is also a challenge also to have an accurate, basically, measurement considering noisy signals.
Great. Thank you so much, Dr. Mohammed. I think we're going to wrap the webinar right now, and you will receive a nice plaque from UND and assigned by our dean and also a letter. So thank you so much for
Thank you very much.
being part of this webinar, and we look forward to work with you in future and maybe collaborate on some work.
Thank you very much. It's my pleasure, and thanks for inviting again. And we look forward to work with you in the future.
Thank you.
Thanks.
Take care.